This is Fundamental Problem 19 from Chapter 16. At the instant shown, end A of the rod has the velocity and acceleration shown. Determine the angular acceleration of the rod and the acceleration of end B of the rod. So we have the acceleration of point A and the velocity of point A given to us. And we are going to use equation 16-18, where we have the acceleration of point B is equal to the acceleration of point A plus the angular acceleration of the rod crossed with the position of B with respect to A minus the angular speed of the rod squared times the position of B with respect to A. So we have that equation here. In order to use this equation, I have to find the angular speed of the rod. Because they give me the velocity of point A, I can do this, and I'm going to do this using what we learned in the previous section about the instantaneous center of zero velocity. So first I have to locate the instantaneous center of zero velocity. So I know roller B is going to be moving horizontally to the right. Roller A is moving straight downward. So if I draw a line which is perpendicular to the velocity of B and perpendicular to the velocity of A, those lines intersect here, and this is my instantaneous center of zero velocity. The distance from A to the instantaneous center, because we have 4 meters here and 5 meters here, this distance is 3 meters. And my equation for the velocity of point A, using the instantaneous center of zero velocity, I have the velocity of point A is equal to the angular velocity of the rod crossed with the position of A with respect to the instantaneous center. Remember that this came from equation 16-16, when point A, and this equation is the instantaneous center, and point B is A for our problem. And because the velocity of the instantaneous center is 0, that leaves us with what we have here. Now, the angular velocity is pointed in the k-hat direction, like this. And if I cross that with the position vector here, which goes from the instantaneous center to point A, so that's in the negative I-hat direction. So k-hat crossed with negative I-hat gives me the velocity going straight downward here. Since those vectors are all perpendicular to each other, I can say the angular velocity of the rod is equal to VA over RAIC. And that gives me the angular speed. We already said that was going in the negative k-hat direction. Since we're going to square it in our equation here, it does not matter whether it's going in the positive k-hat direction or the negative k-hat direction. VA, they told us, was 6 meters per second. And the position of A with respect to the instantaneous center is 3 meters. So that gives us 2. The meters cancel out. We're left with seconds in the denominator, and we can put radians into the numerator. And that gives us the angular speed. And if you want to keep track of these things, this is in the negative k-hat direction. Okay, so now we're going to go back to equation 16-18, which we had up here. And I think at this point we have everything that we need in order to be able to successfully use this equation. So the acceleration of point B, that either has to be in the positive I-hat direction or the negative I-hat direction. It looks like it's going to be in the positive I-hat direction, but if we just say AB is the component, if it's in the negative I-hat direction, we'll just get something negative for that component. Then we have the acceleration of point A, which is 5 meters per second downwards. So we have negative 5 meters per second squared, j hat, plus the angular acceleration of the rod, which is what we are looking for, that angular acceleration is either going to be in the positive k-hat direction or the negative k-hat direction, since the rod is rotating like this. So I'm just going to call it alpha k-hat. And if it's in the negative k-hat direction, then this component will come out to be negative. So the angular acceleration only has a k-hat component. We cross this with the position of B with respect to A, so pointing to B from A. That's like this. That's the position of B with respect to A. So that's pointing in the positive I hat and the negative j hat direction. So this is crossed with my position vector here. In the I hat direction, it's going 3 meters. So this is 3 meters in the I hat direction, minus it's going down 4 meters in the j hat direction. So that's this here, minus the angular speed squared, which is 2 radians per second squared. Or you could stick the negative sign in here, and when you square it, it still comes out to be positive 4. Then we have the same position vector that we had over here, so that's the same thing that we had here. This is 3 meters I hat minus 4 meters j hat. So now I can go ahead and do the cross product here and distribute the 2 radians per second squared that I have here. So I'm going to rewrite the equation doing that. So I have minus 5 meters per second squared j hat. For the cross product here, I have k hat crossed with I hat. K hat crossed with I hat gives me positive j hat. So that's plus 3 meters times alpha in the j hat direction. Then I have k hat crossed with j hat, which gives me negative I hat, but I have the negative sign here also. So k hat crossed with j hat gives me negative I hat, but the whole thing turns out to be positive because of the negative sign that I have here. So that's positive 4 meters times alpha. This is in the I hat direction. Minus the 2 radians per second squared gives me 4 radians squared per second squared. I don't want to keep the radians squared because I have meters here, so we'll throw the radians away and distribute the 4 divided by second squared times 3 meters. 4 times 3 gives me 12, so that's negative 12. That's going to be meters per second squared. In the I hat direction, the negative 4 per second squared times the negative 4 that we have here is going to turn out to be positive, and that is 16 meters per second squared in the j hat direction. Now, if my units work out correctly, on the left-hand side, I have the acceleration, which should be in meters per second squared. I have meters per second squared in this term. This is meters times the angular acceleration, which is going to be in radians per second squared, and we'll throw the radians away, and that will leave us with meters per second squared. Same thing for this term here. This is in meters per second squared, and this is in meters per second squared. So the units work out correctly, and if you want to leave the units out until the very end, you are free to do that. And now we're going to look at the I hat terms and the j hat terms separately. So for the I hat terms, we have the acceleration of b in the I hat direction. Then we have plus is equal to 4 meters times the angular acceleration in the I hat direction minus 12 meters per second squared in the I hat direction. This equation will allow me to find the acceleration of point B if I know the angular acceleration, but I don't know that yet. So I'm going to have to look in the j hat direction. And on the left-hand side of the equation, I have no j hat terms. So this is just going to be 0 in the j hat direction, is equal to minus 5 meters per second squared. And I have plus 3 meters times alpha, and then I have a plus 16 meters per second squared in the j hat direction. Now I can solve this for alpha, so let's bring the minus 5 meters per second squared over to the other side where it becomes positive and subtract 16 meters per second squared from both sides. So I have 3 meters times alpha, and let's leave the j hats out. And then on the other side, this would be 5 meters per second squared minus 16 meters per second squared, which gives me 11 meters per second squared. Therefore, alpha must be equal to 11 meters per second squared divided by 3 meters. The meters cancel out, and I'll stick radians in the numerator for the units. 11 divided by 3. Oh, whoa. I left out a negative sign there. So this is negative, and this is negative, and this is minus 3.67 radians per second squared. So remember, back up here, we said this was the k hat component of the angular acceleration. If it turns out to be negative, your rotation is in the negative k hat direction. So let's write this as a vector. So alpha is equal to negative 3.67 radians per second squared in the k hat direction. So this is one thing that we're asked to find. So we found that, and we also have to find the acceleration of point B, which we're going to get from looking at the I hat component. So now this comes down here. Let's leave out the I hats and just write this as the acceleration of B is equal to 4 meters times the angular acceleration, which is negative 3.67 radians per second squared. This here, we already took care of the direction, right? So the alpha that we have here is just the component that we had here, which is negative. So this is minus 3.67 radians per second squared. Then I have minus 12 meters per second squared. Meters per second squared, and that is going to give me something negative for the acceleration of B. The 4 times the negative 3.67 minus 12 gives me negative 26.7 meters per second squared. And going back up here, this was the I hat component, and we said the acceleration of B was just in the horizontal direction. So we could say AB I hat, or I could just call that the vector AB. And this is going in the I hat direction. And that is the second thing we were asked to find. And because this is negative, this means that the acceleration of roller B is pointed this way. So for the acceleration of point A, it's pointing downwards. For the acceleration of roller B, it's pointing to the left. So that concludes fundamental problem 19 from chapter 16.